Take two continuous streams of high-speed vehicles and force them to cross the exact same physical space. Without intervention, this guarantees a collision. This brings us to the core objective of Highway Engineering Unit 3, managing the safe and efficient movement of vehicles precisely at the locations where traffic streams merge, cross, or terminate. We visualize this problem through this schematic, showing conflict points. These red dots represent the exact coordinates where every trajectory of a crossing, merging, or diverging vehicle overlaps. Engineers use this standardized communication system to precisely manipulate driving behavior and impose geometric order. We are going to build the engineering logic of traffic control from the ground up. We will start with the geometry of passive signs, move into the temporal mechanics of automated signals, and finish with the static demands of parking storage. Solving the intersection problem requires escalating levels of intervention. The guiding principle is efficiency. An engineer systematically removes driver autonomy only when mathematically justified by the data. Let's begin building our theoretical intersection with the first and least restrictive tier of intervention, passive control signs. Looking at this manual diagram of regulatory signs, we see the highest level of passive control. Violating these strict parameters is a legal offense. Notice the precise geometry. The octagon is universally reserved for stopping, while circular shapes with thick red borders designate absolute prohibitions, dictating exactly where a vehicle cannot enter. But an intersection also requires drivers to anticipate hazards before they arrive. This is the role of warning or cautionary signs. This chart shows their strict geometric standard, the equilateral triangle. These rely entirely on driver observation and voluntary deceleration. The final category is informatory signs. As detailed here, these use a rectangular geometry. By guiding routing in advance, they induce driver hesitation, allowing the traffic stream to maintain continuous flow. Passive signs are highly efficient. They rely on spatial separation and driver autonomy. But when traffic volume exceeds a certain physical threshold, spatial separation collapses. When volume reaches that critical threshold, passive signs can no longer prevent gridlock. The intersection physically fails. To solve this, engineers introduced the traffic signal, enforcing strict temporal separation. This control relies on exact parameters. A cycle is one complete sequence. A phase is the green time allocated to a movement, and the clearance time, the amber transition, safely flushes the intersection before the opposing phase begins. But it is an engineering reality that signals are a compromise. They are not a perfect, universally beneficial solution. Reviewing the textbook advantages, signals yield a significant reduction in severe right-angled collisions. However, looking directly at the disadvantages, point 1 dictates that rear-end collisions will likely increase. We are forcing a flowing stream of vehicles to come to a sudden, mechanical stop. Signals also mathematically guarantee delay. Engineers attempt to mitigate this through fixed-time signals, which run on predetermined loops, and traffic-actuated signals, which use physical roadway detectors to adjust green phases based on real-time vehicle demand. When we zoom out to multiple intersections, engineers apply network coordination systems, like simultaneous, alternate, and progressive systems, to link the timings and restore a degree of continuous flow down an entire corridor. Because a signal guarantees a certain amount of delay and introduces the risk of rear-end crashes, it cannot be installed simply because an intersection feels busy or chaotic to it. This raises the critical question: if an active signal inherently causes delay and shifts the collision type, how does an engineer objectively justify installing one? Engineers rely on warrants, strict minimum data thresholds shown in this manual. The first is minimum vehicular volume over an 8-hour period. The second is interruption of continuous flow, where cross-traffic suffers documented delay. Finally, the safety warrant. A signal is justified only if passive signs have failed to decrease accidents over 12 months. A traffic signal is a severe restriction of flow. Treating it as a default safety upgrade is a fundamental engineering error. It is deployed only when the hard data demands it. Navigating an intersection is only the dynamic phase of a trip. Every vehicle that is processed through a signal network must eventually reach a destination, stop, and be stored. This image captures the real-world consequence of high traffic volume arriving at a destination. The spatial footprint required for static vehicle storage is massive. Engineers quantify this using parking studies. This involves two distinct tasks: measuring the actual demand for spaces and measuring the physical inventory available. Looking at the methodology for parking demand, engineers use cordon counts, tracking vehicles entering and exiting a zone to calculate the exact accumulation of cars needing storage. They balance this demand against the parking space inventory, which requires surveying every available curb and off-street facility to determine physical holding capacity. If an engineer fails to balance parking capacity with demand, the resulting circling traffic creates a parasitic load on the local network. These roaming vehicles consume the specific green time intervals allocated to through traffic, degrading the performance of the entire engineered corridor. Zooming out from a single intersection or a single parking lot, we can see the entire urban road network for what it is: a highly interconnected organism. At the base level, we utilize the standardized geometry and color of passive signs to regulate driver autonomy efficiently, solving minor conflicts without stopping momentum. When volume overwhelms that system, we apply the active compromise of signals, stripping away autonomy and using automated phases to trade travel time for right-angle safety. And all of that dynamic routing serves no purpose if we lack the static data of parking studies to safely absorb the volume at the end of the line. High-level highway engineering is the rigorous, data-driven synthesis of these exact control devices. It is the math required to master both the movement and the storage of mass transit.